All right, onward to part C of lecture 20. Now, in the last couple of lectures, we've been looking and using the periodic table, right? So that's what we're going to be doing in this lecture as well. We're going to go back and talk more about the periodic table. It's not really related to what you heard in parts A and B. The only way it's related is it deals with the periodic table again. All right, so it's a few more ideas, a few more terms that involve the periodic table. So let's go ahead and get into them. Okay, so we're going to get into three periodic trends. The first one we'll be talking about here in just a minute is atomic size, and then we're going to talk about ionization energy, and then finally metallic character. So a periodic trend, what does that mean just generally? A periodic trend is basically just a pattern that can be determined by, we'll say, looking at the periodic table. Looking at the periodic table. So I'm going to tell you about these patterns in just a minute. Wouldn't hurt. It'd be probably a good idea to have a periodic table handy because you're going to use them for a couple of practice questions, and also you might want to write these trends down on your periodic table. So with that, let's get into them. All right. So starting off with, we're going to talk about atomic size. So atomic size, what does that mean? It basically means how big is an atom? How big is an atom? So not all atoms are the same size. Some are kind of, well, they're all tiny, I guess, right? But some are even tinier and some are a little bigger. So one way that you'll often hear this described, you might hear people say atomic size, but kind of a more common way actually is you're going to hear it called atomic radius. So atomic radius, just to be clear, it's really the distance from the nucleus to an atom's outermost electrons. So, you know, in the middle of an atom, you got your nucleus, that's where the protons are, right? And the neutrons, I suppose. And then outside is the electrons. So how far is it from here to here? What is that distance from the nucleus to the outermost electrons? Now, there is a pattern. If we look at the periodic table, we can kind of guess, we can kind of predict which atoms are going to be the biggest and the smallest. So in the bottom corner here, you're going to see kind of representation of atoms. And the basic way it works is as you go down, atoms get bigger. As you go down, atoms get bigger. As you go across the periodic table, they get smaller. So they get larger. Oops, let me rewrite that. That's a little hard to read. They get larger going down. Yep, I got to twist my hand here. Larger. And they get smaller going across. All right, now, why would that be? Well, one reason that is going down, that might be a little easier to understand. You know, as we go down, as we talked about previously when we were doing electron configurations, every row corresponds to a different shell. So as we go down, we're using the first shell, and then the second shell, and the third shell, and the fourth shell. So every row that you go down, you're going to a further away shell. Now, so that further away shell, that's going to make the atom bigger. Now, why would it get smaller going across? That might be the trickier one to understand. And the reason why it gets smaller going across, for example, if we go across the third row here, the reason why that's true is all of these guys are putting electrons in their third shell, right? 3s1, 3s2, 3p1, all that. So we're using the same shell, but what happens is the number of protons goes up. So those electrons pull those, the protons, I should say, pull those electrons in, and that actually shrinks the size of an atom. Now, when we go to the next row down, though, we start using a further away shell. And then as we go across, the shell stays the same, but it kind of gets pulled in a little bit because we're adding more and more protons as we go across. So that's kind of the reasoning behind that. this pattern. Going down, you're using a new shell. Going across, you're in the same shell, but the shell gets sucked in by the protons, having more and more protons as we go across. All right, let's move on to another pattern. So another pattern is called ionization energy. So ionization energy is basically how hard is it? What is the energy it takes to remove an electron from an atom? How hard is it to remove an electron from an atom? So we would be looking at basically this reaction. I take something like sodium and I give it some energy. Maybe I heat it up, maybe I don't know, shine bright light on it, something happens. So if I give it enough energy, what'll happen is the sodium will let go of one of its electrons. And by the way, when that happens, if you lose an electron, what is that going to make you? It's going to make you a positive or negative. Oh, if you lose an electron, it's going to make you positive. So we would form like a sodium ion. Okay, we'd form a sodium positive ion. All right, so doing this, making an electron get ripped off from an atom. Well, some atoms do that easier than others. So there's a pattern. And the pattern is as you go down, it gets easier. So ionization energy decreases. I'll just write IE, decreases. So it gets easier. And as you go across, ionization energy, it actually gets harder to remove an electron. Ionization energy increases. Oh, I guess it says it on the chart, but I'm just rewriting it just to make sure. Okay, so the pattern is it gets easier going down and it gets harder going across the periodic table, ionization energy. All right, one last pattern. One last pattern is called metallic character. All right, so metallic character, that's going to be what you might guess, which is, are you like a metal? So are you shiny? Are you a good conductor? All those things that we talked about that makes metals metals. Now, this pattern, again, there is a pattern looking at the periodic table. And that pattern is, as you go across, things become less metallic. Shouldn't be a big surprise, right? And in fact, over here in this corner, these guys are non-metals. So as we go across, metallic character, I'm going to write MC, decreases. You become less and less like a metal. And as you go down, metallic character increases. Metallic character increases. All right. So with that, let's go ahead and let's make a little summary of all these patterns, okay? So let's see if we can put them all together into like one idea, one chart, okay? I'm going to do that on the next slide here. Okay, so when I've drawn these arrows, like increasing, decreasing, I've done it the way most books do it. Let me show you another way that might make most sense. And that way is I'm going to focus in on this top right corner. And this top right corner, this is where we find the elements in that top right corner that are, first off, they're the smallest. Now, if you put the patterns together that I've talked about, if you go over and down, you get bigger. So as we go this direction, we're getting larger. We're getting larger. All right, you get bigger atoms. So maybe just to be clear, I'm talking about atomic radius, right? So they have the smallest atomic radius up in this corner. As you go across and down the periodic table, you're getting larger atomic radius. All right, now the other patterns, let's see if we can put them on the same chart here for a minute. So the other one we talked about, the next one was ionization energy. So ionization energy, if you're in this top corner, you have the highest ionization energy. And as you go across and down the periodic table, ionization energy becomes lower. Lower ionization energy. I'm just going to write IE for ionization energy. Okay. Now there's one last one, right? The last one we talked about was metallic character. This top corner, these guys have the, we'll say, least metallic character. And as you go across and down, over towards like this corner with francium and all these guys. As you go across and down, you're getting more metallic character. All right, so top corner. These fellas in this top corner, they're the tiniest. They're the hardest to remove an electron from. They also are the least like a metal. And as you go across the periodic table, all of those things change. You get bigger going across, you get easier to remove electrons from, and you get more like a metal. All right. So with that, let's do a little practice questions. We're going to do a couple pop-up questions here. Let's see if this is making sense. I hope it is. All right, so let me flip over and we'll do a couple practice questions. Maybe I'll do one to get you started and I'll give you a couple to think about. Okay, so the whole point of learning about these patterns, these periodic trends, is that you can make some predictions about atoms just by looking at the periodic table. So one, again, is the size of an atom. So the size of an atom, we usually call that the atomic radius. So this question here, they want me to arrange the following elements in order of increasing atomic size. So they want me to go from, I guess, the smallest atom and put them in order to the largest atom. So what I'm going to do is I'm going to find them on the periodic table first. So the smallest atom, and we're going to go to the largest atom. So they want me to think about gallium and fluorine and sulfur and calcium and rubidium. Now, what was the pattern for atomic radius? Well, one way I explain it to you is let's focus in on this top corner. This top corner, this is where you find the smallest atoms, So as we go over and down, over to the left and down, you're getting bigger and bigger and bigger. So the smallest atom would be fluorine, and then sulfur, and then gallium, and then calcium, and then rubidium. Going over and down, atoms get bigger and bigger and bigger. So let's go ahead and list them. What do we say? Fluorine, then sulfur, then gallium, that's a G there, then calcium, then rubidium. Does that look right? I think so. Let's see, fluorine, sulfur, gallium, calcium, rubidium. Yeah, that's the right order. All right, so with that, I've done one. Oh, let's see if this is making sense. So I'm going to give you a couple of questions. We'll do a couple of practice questions, little pop-up questions on this topic. Let me flip over and let me give you one to think about. All right, so another pattern we've talked about is ionization energy. What is ionization energy? How hard, again, is it to remove an electron from an atom? There's a pattern for that. All right, and I want you, in this question, it says, list these, arrange these elements in order of increasing ionization energy. So I want you to give me the lowest ionization energy. Who's the easiest to take an electron from? That'll be on the left, and then you'll list them. The last one on your list will be the highest ionization energy, the one that is the hardest to remove an electron from. Now, in the interest of making this just a little bit easier before you have to answer, let me find these elements on the periodic table for you. We got nickel, we got yttrium, we got cesium, and oxygen, those four. So what's the pattern? I want you to list them, lowest ionization energy to highest. Okay, hopefully you got that one right. All right, so yeah, there's a pattern there, right? So there should be a pattern there, and I guess, let's see, what was that pattern? The pattern was, well, the guys in the top corner have the highest ionization energy. And as we go over and down, you're going to get lower ionization energy. So I want to list the lowest one first, actually. So I should probably have drawn the arrow the other way, hadn't I? So the lowest one would be cesium. That's the easiest to remove an electron from. And then we go to yttrium. And then we go to nickel. And then we finally, the one that'll be the hardest to remove an electron from would be oxygen. So that should have been your answer, I hope. All right. All right, let's try one last one. One last question about these patterns. All right, let me flip over here. And this one, I get you 3 elements. Who's the most metal-like? All right, who is the most metal-like? So you don't have to even list them this time. Just tell me there's 3 of them. Who's the most metal-like? Barium, oxygen, or cobalt? Oh, how did that work again? Going over and down. How does that work? Over and down, you become more metal-like, more metallic character. So the one that would be the closest to that, I guess, bottom left corner is going to be barium. It has the highest metallic character. All right, with that, oh, I got one more pop-up question for you. Okay, hopefully you got that one right too. All right, so that's it for this lecture. We're done with lecture 20. Yay! All right, if you have any questions, of course, just let me know and I'll help you out the best I can. All right, hopefully you're having a good day. I'll see you again soon.